Good day, everyone. In this lecture, we'll consider superposition and source transformation methods. In our signals and systems course, we established that for superposition principle to apply, the system must be linear. So, in other words, here, for superposition principle to apply, first, the system must be linear. And for the system to be linear, then it must obey the principle, or better said, the law of additivity and the law of homogeneity. Okay, it's the same thing as scaling. But in electrical circuits, we say that the circuit itself is linear if it consists of independent sources, linear elements, and linear dependent sources. So, since the most important consequence of linearity is the principle of superposition, the implication is that superposition does not apply to nonlinear circuits. Good. So at this point, we must note that linear elements are passive elements that exhibit linear voltage-current relationship. Okay, so the linear voltage-current relationship implies that the law of additivity and the law of homogeneity applies. So, for instance, the law of homogeneity applies if the scaling of the current through the element results in an equivalent scaling of the voltage across the element. So let's assume we have a system here, and then we say current I flows through such that the voltage across the terminals is V. Should we scale the current that flows through the system by some parameter K, then we'll also observe that the voltage measured across the terminal has been scaled by that same parameter K. So now, should this occur, we say that the law of homogeneity has been satisfied. And that is the multiplication of the current through the element by a constant parameter K results in the multiplication of the voltage across the element by that same parameter K. Okay, and in a similar way, should we observe that the sum of current flowing through a particular system, then should the system be linear, then we should also measure the sum of the voltages across the element. Now, should I1 plus I2 flowing through the system result in the sum of I1 and the sum of V1 and V2 across the terminals, then we'll say the law of additivity is satisfied. So, when should we consider the utilization of superposition method. So when should we consider the utilization of superposition method? I will say that the superposition method provides a systematic approach for analyzing multi-source circuits, okay? Multi-source circuit. So when we have multiple independent sources in the circuit, then the superposition principle may be sufficient. So let us look at some of the basic steps in applying superposition method. Okay, so let's say steps required to apply superposition method. So the first point here is that since we have multiple independent sources in the circuit, then we want to apply each source at a time. So here we apply one of the independent sources while setting the other independent sources to 0. Okay, so let us assume we have a circuit that looks something like this, plus minus. So here we have 3 volts voltage source, then we have 2 ampere current source, plus minus. So across this terminal, we have V0, then here 2 V0, it's a dependent voltage source, then here we have 2. So it is expected that now here we're expected to measure the V0, the voltage across this terminals. Now since we have multiple independent sources, so the point is each source has to act alone. So should we adopt the 3 voltage the 3 volts voltage source, then we'll have to deactivate the current source. And then to deactivate the current source, we'll replace it by an open circuit as the current source, right? So to deactivate the current source, we'll replace by an open circuit. So meaning we want to draw something like this because the open circuit here. So open circuit looks something like this. Because here we're saying that I is equal to 0 because R extends to infinity, and I is the same as V over R. So V over infinity will definitely tend to 0. Okay, so we end up drawing the circuit plus minus 3 volts acting alone, plus minus 2 V0, then minus. So once we activate the voltage source, then to deactivate the current source, replace by an open circuit. Then secondly, to deactivate the voltage source, replace by a short circuit. So once we replace by a short circuit, we say V is the same as 0, because in this case, R is assumed to be 0. If we have perfect conductor, then the resistance tends to 0, and when V is same as IR, and the I times 0 will give us 0 volts, right? So when the current source acts alone, then we can replace the voltage source by a short circuit. Then current source here. Okay. So remember, what we want to measure is the voltage across the stem. Then the next point be to relabel voltages and currents using suitable notation. So we relabel voltages and currents using suitable notations. So in this case, since we want to measure V0, so when the voltage source acts alone, say we say V01. When the current source acts alone, say V02. Then afterwards, we analyze the simplified circuit. Okay? Analyze the simplified circuit to estimate required current or voltage. Then we want to repeat step 1 through 3. Steps 1 through 3 until each independent source has been considered to act alone. So afterwards, we add partial currents or voltages obtained from the separate analysis. Okay, so in this case, in our case, V0 will be the same as V01 plus V02. So in this case, we have V0 to be the same as V01 plus V02. Now, if we had more than 2 independent sources, say 3 independent or 4 independent sources, then we may end up adding up about 3 to 4 partial voltage values. What if it was current we had to measure? Probably current flowing through some element in the circuit, then it will be I01, I plus I02 plus I03. Okay, so it will be what? Now, it should be noted at this point that the dependent sources were left unaltered. Okay, so note, while deactivating the independent sources, note that the dependent sources in the circuit are left unaltered. Okay. Good. Then also note that power is nonlinear. Okay. Since power is not a linear quantity, we cannot add up partial power values. So as once we are able to investigate the resultant voltage value, and better still, the resultant current value, then the product of the current and voltage values of the resultant current and voltage values gives us the power value. Okay? So this implies that step 5 does not apply to power quantities. Let us consider an example. So let's assume at the circuit so 3 volts, 3 ohms, 3 V here to measure. So one estimates V0 using superposition method. Now note that nodal analysis can be used here. Okay, and should we consider this as a super mesh? Then mesh analysis could also apply. Now that we want to apply superposition principle, we have two independent sources. So our resultant voltage V0 is going to be the sum of the partial voltage values. So when the 3 volt source acts alone, so when 3V source acts alone, what do? We deactivate the current source, and if we don't want current to flow, all we need to do is to yank off the 2 amp current source. So we'll replace by an open circuit. So let's withdraw. It's minus 3 volts. Plus minus 2V0. So replace the current source by an open circuit. Then we relabel, so this will be V01. Okay. Now, if we use mesh analysis here and assume I flows in this direction, you'll observe that there's an open circuit. When there's an open circuit, means it means current does not flow. So in this case, I is equal to 0. Okay, so that will be, so this is going to be plus minus here. So this will be minus 3 plus, sorry, that's 3 on here. Then minus 3 plus 3I, 3 times this, that's the voltage, plus this plus sign here 2, V0, 1 now, because we are relabeling all the voltage values. So that will be 2V01, then plus V01, V01 is equal to 0. Okay, now this is our first equation here, this is our second equation here. So if we substitute for I, since no current flows through the open circuit, so there's a current flowing here 0. So that will be minus 3 plus 3 into 0 plus 2 plus 1, 3, V0 1 is equal to 0. That's minus 3 plus 3 V0 equal to 0. So V0 1 is the same as minus 3 V0 1, 3 minus 3, that's V0 1. Sorry. Okay. So V naught 1 is minus 3. And this crosses this, that's minus 3 V naught 1. So 3 minus 3 divided by minus 3, that's 1. So V naught 1 is equal to 1 volt. So when the voltage source acts alone, then that is what we get. Okay. So what happens when the current source acts alone? So for us to replace the voltage, to deactivate the voltage source, we replace by a short circuit. So when 2 amp source acts alone, then the voltage source will be replaced by a short circuit. So we have a short circuit here. Plus minus 2 V naught. This is 3 ohms. So it's 2 ampere. So this time current source is acting alone. So we have V naught 2. So this will be 2 V naught 2. Good. Now, should we consider these as two separate loops? Then we have a current source between two different loops. That gives us enough reason or justification to apply super mesh. So this now be our super mesh. Then I flows, right? Good. Now by KVL, around super mesh, this is plus minus. So that will be 3I plus 2V naught 2 plus V naught 2 is equal to 0. So 3I plus 3V naught 2 is equal to 0. Now you observe that the 2 amp current flows in this direction. Okay, it comes up here, it flows up here. This is a node. Now, ideally at the node, the current is supposed to split into two different directions, but this is an open circuit, so no current flows through the open circuit, so the entire current flows in this part. Okay. Now you observe that the direction of current flow of the 2 amp current flow is in the opposite direction with the super mesh current. Okay, so this is 2 amp flowing. So it means that I is the same as minus 2 ampere. So if we substitute that into this, so that will be 3 to minus 2 plus 3 V naught 2 equal to 0, minus 6 plus 3 V naught 2 equal to 0. So that will be minus 6 equal to minus 3 V naught 2. Then V naught 2 be minus 6 divided by minus 3, which is 2. So V naught 2 is the same as 2 volts. So by superposition, V naught is the same as V naught 1 plus V naught 2, which is 1 plus 2. That gives us 3 volts. Very simple. So let us consider source transformation. Now, in order to appreciate the ideology behind source transformation, it will be necessary to investigate the difference between the ideal and practical sources under load conditions. Okay? Because the source transformation itself actually gives the idea that a current source can be replaced by a voltage source and vice versa in a circuit in attempts to simplify that circuit. So let us split the board to halves. Okay. So recall that an ideal voltage source minus looks something like this. Okay, perfect. Now, if we consider an ideal voltage source under load condition, so it means that we want to connect this to a load, so we have plus minus, then so we have a load resistor, to do it this way, RL, and that is the source voltage. So let's assume current flows in this direction from negative to positive. So by Ohm's law, I is the same as Vs over RL. And now, what's the limitation here? Now, the limitation here is that when RL is the same as 0, that is replaced by a short circuit, then I will be seen to tend to infinity. And we know that infinite current is not realizable in practice. So how do we limit this infinite current? So this brings us to a practical voltage source. So in order to model a practical voltage source, we now have to connect a resistor in series with the voltage source so as to limit the current. So we're going to have practical voltage source connected to a load looking something like, so in other words, practical voltage source will now look something like this. Okay, this is RS, this is VS. So if we connect this to a load, plus minus, so in that load condition, so the RL, so RS, and this will be VS. Okay, then current flows in that direction. So in this case, RS is the internal resistance, okay? RS is the internal resistance that limits the current from extending to infinity, okay? Now, if we measure the voltage across the load, so by voltage divider rule principle, VL will give us RL divided by RL plus RS VS, okay? So if we rearrange this, so this will give us more like VS RL by RS plus RL. Perfect. Now let us consider the ideal current source. Now we know current source looks something like this, right? So if we consider ideal current source under load condition, then This is RL. Okay. Now, this is IS flowing to the circuit. So, this terminal, we could measure V. So, by Ohm's law, we know that V is the same as IS RL. Okay. But once again, there is a limitation to this. Okay. What's the limitation? So, when RL tends to infinity, that is, it is replaced by an open circuit, we'll see that V will be IS times infinity, making it tend to infinity. So V here is equal to infinity. And we know that infinite voltage is not realizable in practice, okay? Infinite voltage is not realizable in practice, okay? So we want to limit this infinite voltage value. And to do that, we connect a resistor in parallel with the current source. Then we're going to have something like this. So that brings us to the practical current source model. Then we have something like this. RS. Okay, and here RS is the internal resistance. Okay, so to compare the response, let us now connect a load to this practical model. So under load condition, what do we get? That is current source, the practical model, then we have the load. Here RL, this is RS, this is IS. Okay, so by inspection, you see that the current here, if IS flows here, then IL flows here. Okay, so by current divider rule, by current divider rule principle, we know IL is the same as 1 over RL RS plus 1 over RL times IS. So that is going to give us RS plus RL IS. Okay, and now by Ohm's law, to investigate the voltage that is across the load, knowing that this is a node, we know the same voltage we apply across RS and R. So we know that VL is the same as the current flowing through the resistor IL times the resistance value. And we already know IS, so it means IS is RS over RS plus RL IS times RL. So VL is seen to be the same as IS times RS and RL divided by RS plus RL. By inspection, you see that this equation And this equation will be similar if Vs is the same as Is Rs. Okay, so at this point, you'll see by comparing the voltage across the load resistor, RL, based on the outcomes from the practical voltage source and the practical current source, then these two models will be similar if Vs is the same as ISRS. So, if the source voltage Vs is related by Ohm's law with the current Is, then both models could be replaced with, or could be considered to be comparable, meaning they are equivalent. So this is what, meaning the practical voltage source is therefore equivalent to the current, to the practical current source. This is Rs, S, this is Rs, this is Vs. If Vs is the same as Is Rs. So technically, Is will be the same as Vs divided by Rs, where Rs and Rs are the same, and why Vs will be the same as Is times Rs. Now this is what we refer to as source transformation. So therefore, the source transformation method therefore implies that a practical voltage source may be replaced by a practical current source, and vice versa if and only if the sources, that is voltage and current, sources are related by Ohm's law. So what are the basic steps? Basic steps for source transformation. Let's consider a few steps. So the first step here is to perform repeated conversion from repeated conversions between the practical voltage source model and the practical current source model using Ohm's law to relate the voltages and current. So this repeated conversion is done until the circuit is simplified to a single source and a single resistor. Okay, so meaning that we have a single resistor connected in series with the voltage source, or a single resistor connected in parallel with the current source. And then the next point to take note of is using the Kirchhoff voltage law, the KVL, you add series voltage sources. Don't forget that the voltages applied across nodes is the same. So all elements connected in parallel having a common node have the same voltage applied across their terminals. So you can only add voltages in series connected elements. And also using KCL, Kirchhoff's current law, we add parallel current sources. Beautiful. So let's consider one example. So let's assume we have so this is 12 volts, this is 2 ohms, this is 4 ohms, this is 24 volts, this is 6 ohms. So we want to calculate the voltage across the terminals. Now, by inspection, we observe that the 4 ohm resistor and the 2 ohm resistors are connected in series with the 12 voltage source, and the 6 ohm resistor is connected in series with the 24 volts voltage source. So technically, recall that we could replace the voltage source connected in series with a resistor by a current source connected in parallel with an equivalent resistor. Where RS, this is IS, VS, provided they are related by. So here we could replace this by a simpler circuit. So let's lock this up here. So now we replace this entire model by simplified circuit. Here we have a single voltage source and a single resistor. Then same here. Also minus V. So this is 6 ohms. This is 24 volts. This is 12 volts. And then this is 4 ohms plus 2 ohms. That's going to give us 6 ohms. Now, the So we have 24 volts here, 6 ohms, we have 6 ohms here, we have 12 volts. So we can replace this, the current source, from negative to positive, so the arrow is going upward. So that's a direct current direction. It is parallel connected resistor. This is for the first one. And similarly for the second, then we have another 6 ohm resistor. So what we are after is to estimate V. Okay? This is plus minus V. Okay? Now, we were told that Vs is related to Is by Ohm's law. So this current value for this connection will be Is the Vs over Rs, which is 12 over 6. 12 ohms, 12 volts divided by 6 ohms. So that will give us 2 amp. Why? For this connection, so we have this. So this point, we're going to be having 24. That's 24 volts, right? Divided by 6 ohms. That will give us 4 amp. So we have 4 amp. So what we now have is the current source, parallel, the 6 ohm resistor, this is 2 ampere. And the current source, this is 4, okay, 6 ohms, right? And this is plus minus B. Now, understand this is a node, right? It's a node. So the total current flowing in is the same by KCL. Sum of current in is the same as sum of current out. But in this case, the total current flowing in is 2 plus 4, right? 2 plus 4. So that is 6 ampere is flowing in. So we can replace with a single 6 ampere, right? 6 ampere. Then we have 2 resistors connected in parallel. 6 ohms, 6 ohms, right? So we've applied one of the 3 laws, 3 principal steps, plus minus V. Okay. Now we know that 6 is in parallel with 6, so that's going to give us 1 over 6 plus 1 over 6. That will give us 36 divided by 12, which is 3 ohms, right? So that will give us 3 ohms here. Okay, so now we can draw a circuit 6 ampere. It's in parallel plus minus 3 ohms. Now this is equivalent to current to a voltage source connected in series with the 3 ohm resistor. And once again, the voltage here is related by V for the ISRS. So that is 6. As for this, that's 6 ampere times 3 ohms, which is equal to 18 volts. So this is 18 volts. Okay. So means that we now have this to be the same as plus minus V, 18 volts, 3 ohms. Well, notice this is an open circuit, no current flows across, no current flows through this 3 ohm resistor. So I is equal to 0. So V3 will be 3 times 0, which is equal to 0 volts. So the voltage across the 3 ohm resistor is 0. So the entire voltage is seen to be applied across the terminal, so that V is the same as 18 volts by source transformation. Okay? And we could actually check this from this circuit. Then we have the 6 ampere, this parallel combination. This is 6 ohms, this is 6 ohms, right? Fine. Now, by current divider rule, what do we get? I prefer to use the standard approach rather than the short formula. It's 1 over 6. That's the current flowing through this, right? And so this is I6. So I6 is 1 over 6, 1 over 6 divided by 1 over 6 plus 1 over 6, 1 over 6 plus 1 over 6 times 6 ampere, right? So that's going to give us 36 divided by 12, which is 3 ampere, right? And now, the voltage across this 6 ohm resistor, the V equal to I6 times 6 ohms, right? Which will be 3 times 6, which gives us 18 volts. And that is the voltage across this terminal, which is the same voltage across this terminal. So meaning this is fully validated by different methods. This is a good place to stop, and hope to see you in our next class. Bye.